Okay, oxidation reduction reactions. This is the final unit in our class here this year, redox reactions. So we are starting this today in your Glencoe text, chemistry text, matter and change. We are in chapter 19. So you can check that out. You can have your chapter 19 open to follow along. Some of the diagrams I'm going to show you here on the screen may or may not be in your notes that I've given you, but they will be in your textbook, most of them. So let's talk about what redox reactions are. So oxidation reduction reactions, or reduction oxidation reactions, that's where we get the redox from. I will refer to them as redox reactions from now on, and that's what they mean. They are a specific type of reaction where something is reduced and something is oxidized. So let's just venture back into the recent past and consider what we've studied before. If you remember in Physical Science 20, or maybe even before that for you, we've studied different types of chemical reactions, okay? So some of the different types of chemical reactions that we've studied in the past would be synthesis, okay, where we have, let's say a simple synthesis would be two elements or whatever combining to form a single compound, synthesis. And that's what we have down here as the example that you can see at the bottom of the screen. Decomposition, that's the reverse process. We have a compound that breaks down into two or more simpler parts. Single and double replacement, all right? A lot of the reactions that we see today are single double replacement. Combustion, okay, so where we have a hydrocarbon and oxygen producing carbon dioxide and water. Acid-base reactions, which we just got finished that unit, so you know a lot about those. So some of these reactions also involve a transfer of electrons between atoms. Now, not all of them do, but some of them involve a transfer of electrons, and we'll talk a little bit more about what that exactly means. Oxidation reduction reactions, or redox reactions, are a type of chemical reaction that involves a transfer of electrons between two species. So let me just show you an example, and you probably recognize this example. We've done demonstrations like this in class before, where I've taken a magnesium strip that is Mg solid, and I've lit it on fire, burned it, and allowed it to burn. So the chemical reaction that accompanies that demo is Mg, magnesium, plus oxygen gas produces MgO, magnesium oxide, solid. Now, the solid is the white flaky stuff that appears. Obviously, there's heat, there's light, and there's some of this smoke. There are other secondary things that would come about because of the burning in air and all that sort of stuff. But this is the main reaction. Now, in the past, we've focused on this as being a synthesis type reaction, right? A synthesis. We have magnesium and oxygen combining to form this compound. That's a synthesis reaction. But also, it's also a redox reaction. And why is that? Well, if you look at this diagram, is this in your notes? Do I have this copied in your notes or not? Yes? Okay. I don't know if it's too small for you to see or not, but consider this. If we have Mg, and of course the balance equation would be 2Mg plus 1O2 plus, produces 2MgO. But if we have two magnesium atoms, like you see right here, magnesium atoms right here, those are neutral atoms. Same number of protons and electrons, they are neutral. What happens, though, is when magnesium combines with oxygen, electrons are transferred. Now, how do we know that? Because MgO is an ionic compound. You know that magnesium forms a 2+ ion, and oxygen forms a 2- ion. That's the reason why it's written this way, Mg1O1, because of the +2 nature and the -2 nature, right? And so how did magnesium, a neutral atom, get to be magnesium ion? Well, it became a 2+ ion because it gave up 2 electrons. This happened twice. And so this is what we have as a visual representation of this equation. So the important thing here is to identify or to realize that Mg in its elemental state, it's neutral, it's a solid, the magnesium strip, and it becomes magnesium ion within an ionic compound. And so there's a transfer of electrons. So these are both neutral. The magnesium gives up electrons. The oxygen accepts the electrons to become ionic in nature, and then that's how they get together as an ionic compound. Okay? Now, we didn't talk about this at all before. We talked about types of reactions. And again, as I mentioned, the single and double replacement, oftentimes single and double replacement are not redox reactions. You don't have to write this down, but if we have something like, this is off the top of my head here now. But if we had something like CaNO3, I guess that would have to be 2, plus, let's say, NaCl, and that produced CaCl2 plus NaNO3. Okay, we'd have to balance this 2 here and 2 there, I guess. Okay, that looks balanced to me. Yeah, good. Okay, so if you look at this, calcium is an ion here, +2, and calcium is an ion here, +2. Nitrate is a polyatomic ion, -1 each. Nitrate is a polyatomic ion, -1 each, and so on. Calcium is +1 and +1. Chlorine, -1, -1. So in this type of reaction, there is no transfer of electrons in between the elements, okay, or in between the species. It's just simply we have ions at the beginning rearranging with other ions at the end. So this is not a redox, but there are some, obviously, where electrons are also transferred. Okay, do you get the big picture there, what a redox is? It's a chemical reaction involving the transfer of electrons. Okay, so example 2 here, look at this one. If we start with solid sodium and we were to place this in chlorine gas, then we would have a reaction happening and we would have sodium chloride coming out of it. Well, sodium as a solid is neutral. Sodium as an ion is a +1 charge. This is an indication that sodium has given up an electron. Chlorine here is neutral. It's a gas. It's neutral. But over here, this is a chlorine ion. It has picked up an electron. So as you see here, this is sort of the disaggregation of this. NaCl aqueous, remember that's a very high solubility, so it's not a solid, it's not a compound, it's loose. It's kind of the ions are all floating around in solution. So it really looks like this. And here's where you can see that sodium here, solid, becomes sodium ion. Chlorine gas in an elemental form becomes chlorine ion. Okay? So notice that sodium was neutral, then lost an electron. Also, chlorine was neutral, then gained an electron. So when we have a transfer of electrons, something is going to give off an electron or let go of an electron or lose an electron. Something is going to pick up or gain an electron. Now, they do have to be accounted for because in chemical equations, we have to account for everything, right? Whatever we start with, we have to end with. There's no magical formula where something just appears out of nowhere. And so that's going to lead us to considering these electrons in our balancing, but that comes at the end. So what else can we say about oxidation and reduction reactions in general? A redox reaction is any chemical reaction in which the oxidation number of a molecule, atom, or ion changes by gaining or losing an electron. So we're going to talk today mostly about oxidation numbers. And this is basically the accounting system that tells us how many electrons we have in an atom at the beginning and at the end of a reaction. Oxidation number is the charge of a monatomic ion. So like the Na+, the oxidation number for an ion that's monatomic, one atom, this would be +1. The oxidation number here would be +1. Or it's the apparent charge of an element in a compound. And we're going to take a little bit more time today to explore what that actually means. Okay? The apparent charge of an element in a compound. These type of reactions occur every day and are vital to some of the most basic functions of life. Some examples include photosynthesis, respiration, combustion, and corrosion or rusting. Okay, so some of those will be blanks that you'll want to fill in to your notes there. To understand these types of reactions, you must first understand oxidation numbers or oxidation states. Okay, so it'll be referred to oxidation numbers or the oxidation state of an element. Okay, any questions here so far? Any clarification needed, or any questions about what we've talked about here so far? You guys got all the blanks in your notes and stuff? Okay. So redox type reactions are kind of another type, but they overlap with some of the original types that you've learned, okay? So they're kind of another category of reactions. Rules for assigning oxidation states. Okay, so as we mentioned earlier, the oxidation number or oxidation state of an element is the charge of its monatomic ion, or this part here, the apparent charge of an element in a compound. That's what we're going to explore further here now. So how do we find out oxidation states for elements that are inside of compounds? There are some rules we can follow. The oxidation state, OS, corresponds to the number of electrons, and that's e to the little power of negative. Like that's a common, if you guys see that okay? You can cut the lights if you need to, guys in the back. E with the little exponent negative, that's a common notation for electrons that I use all the time. So it's the number of electrons that an atom loses, gains, or appears to use when joining with other atoms in compounds. Tracking oxidation states helps us determine whether a redox reaction has occurred. So we want to track from reactant to product the oxidation states of the elements involved. Okay, so here's the first rule. The oxidation state of an individual atom, not ion, but one single lone atom. So if you have iron solid or oxygen gas, the oxidation state is 0, okay? So anything that's by itself that does not have a charge on it is 0. One single atom, no charge, oxidation state is 0. It's like even, okay? The total oxidation states of all atoms in a neutral species is 0. And the total oxidation states of all the atoms in an ion, let's say it's a polyatomic ion, has to be equal to the ion charge. So if we have something like, now I do have some examples here, and I'll focus on this one first. An example like NaCl, okay? See if we can get that all in one line. NaCl. What, you don't know NaCl here, program? Okay. So the oxidation states for NaCl must add to 0. Why? Because this is a neutral compound. The overall charge is 0, so that means they must add up to 0. Now they both could be 0, but they both could be something else too, right? And so what we see is that in this compound, this is an ionic compound, and so sodium forms a +1 ion. That's really the only option for sodium, and chlorine is a -1 ion. And so the oxidation states for sodium and chlorine would be +1 and -1, or -1. So let me expand on point number 2 here. If we had something like carbon dioxide, this is a neutral compound, right? And so oxygen's states and or number and the carbon number would have to add up to 0, okay? If we have something like phosphate ion, PO4 3-, the oxidation states of the elements involved here would have to add up to 3 negative, or -3, -3, okay? And we'll talk more about that shortly. Let's just go over some more rules here. So number 3, group 1 metals. So that's the alkali metals there on the far left of the periodic table. Right here, group 1. I don't know if you can see that. So group 1 right here. Oops, let's use red. Group 1. These are +1. They form +1 ions. So and they really easily form +1 ions, right? We know about that. They like to give up an electron. They have one annoying electron on the outer level there, one valence electron, and they are more than willing to get rid of it, so they have now a full outer shell, right? So group 1, they always have +1 charge. And group 2, which are the alkaline earth metals, this group 2 here, they form a +2 ions, so they have a +2 charge. Almost always, almost completely exclusively.
Mr. Maxwell?
Okay, so point number 4. The oxidation state for fluorine is -1 when in compounds. Now, fluorine, for sure, generally generally most of these halogens here are -1. Fluorine for sure. H is usually +1. This is kind of a funny spot for H. It can be a -1 at times, but very seldom. Anyway, so fluorine, and most of the time chlorine, bromine, and iodine are also -1. Okay, so these ones are generally -1, but fluorine for sure. Where are we? Hydrogen generally is +1. Oxygen generally -2. So there are some exceptions, but most of the time you can bank on hydrogen being +1, oxygen being -2. So like I say, if we have CO2, right? This is what this means. Generally, oxygen, you can think of oxygen as having an oxidation state of +2. Now, there are 2 hydrogens, so overall, this has a +4, -2, not +2. This has a -2 charge, 2 of them have a -4 charge. And so carbon then, because carbon is a little unknown, you kind of think it might be 4, but this is kind of a double check. So you start with oxygen, you know it's -2. So carbon has to be +4 because this is a neutral compound. You see that? So we're going to practice more of this in a few moments, but you can always start with oxygen. So look at this. In this case right here that I mentioned, you start with oxygen. Phosphorus can have different oxidation states. Oxygen always, most of the time, has -2. So you can go from there to figure out phosphorus. Let's finish the rules and we'll do some examples. Okay, number 7. In binary metal compounds, group 17 elements have an oxidation state of -1. That's the halogens. Okay, so in binary, sometimes in polyatomic compounds, those can change slightly, but most of the time, and especially in binary compounds, those halogens that I mentioned are always -1. And also in binary compounds, these are -2, this group 16 right here, and then group 15 is -3. So generally, most of the time, these oxidation states are the same as the charges that they would typically make as ions. Okay, and we did mention this before, but the sum of the oxidation states is equal or is 0, for a neutral compound, and equal to the charge for polyatomic species. All right, so let's get some practice with these rules. Here's some examples that you should have in your notes. Okay. All right. So, iron. Now, iron is solid. It's monatomic. It has no charge here. So what do you think the oxidation state for this iron solid would be? Shout it out. 0 is correct. It's 0. Very good. What about the oxidation state for oxygen, like O2, as an elemental gas? Now this is where you have to be careful. This is not in a compound, so oxygen is not -2 here. This overall is 0 as well. Yes, very good. So now, this is very much like the first example that we saw, right? So now we have an ionic compound. An ionic compound. So what is the oxidation state for iron now? That is, what is the apparent charge in this compound for iron? What's your guess? Well, what ion is involved in this ionic compound? Is it the 2+ or the 3+? It's the 3+, yes. So iron here has an oxidation state of +3. And that's just for this iron. Okay? And because it's an ionic compound, we understand that oxygen now is really in an ionic form here, or it was just before this happened, and so that's a -2. So iron has gone, Fe has gone from 0 to +3, and oxygen has gone from 0 to -2. Okay? Questions over there? Good question? You missed something? You missed some blanks? Okay, I can go back. Everybody okay with A here though? Okay, B is really easy, right? One of those rules is the apparent charge of the ion, right? So the oxidation state for Fe2+ is 2+. There you go. Okay, now I'm going to give you a minute. I want you to try C on your own, and I'll show you the answer in a few minutes. So pause here and do C. So I want to know what the Ag is over here, and I want to know what the Ag is over here, and see if it's changed. What is the H here? What is the H here? Sulfur and sulfur, okay? So label oxidation states for the elements in every compound that they appear in this equation. All right, so here's what I have here for the solutions. Silver, Ag, has an oxidation state of 0. It is monatomic. It's elemental. There's no charge, so that is 0. What about over here, though? Over here, this is Ag2, okay? So Ag, if you look on your periodic table, it has a charge of +1. If there's two Ags, that would make sense for a sulfur 2- connection, right? So we've got two Ags for one sulfur. So Ag over here is +1. That's the oxidation state for silver. Now, you don't say +2 because there's two of them. We're just talking about the element, the atom itself, okay? So it's 0 over here because it's elemental, it's neutral. Over here, because it's formed a compound due to its ionic state, we've determined that this silver is a +1 oxidation charge. Okay. So hydrogen, well, in H2S, this is a +1. 2 hydrogens for 1 sulfur. Over here, this is elemental hydrogen, so this is 0. S, okay, so according to rule number 5, S has an oxidation state of -2. It has -2 over here, and guess what? It's -2 over here. So there has been no electronic transfer for sulfur here. The two species that have exchanged electrons, though, are silver, right? Silver has lost an electron to become more positive. And hydrogen has gained an electron to become more negative. Okay, so electron has been picked up here. Any questions? Questions, sir? All right. Okay, let's take a look at example 2, if I can move down here. Okay, example 2, assigning oxidation states. Now, what happens if we have a ternary compound or a polyatomic species here, and I am looking for the oxidation state for P here? Well, what you do is you look at the elements that are as well in the compound, and you see if there's rules that apply to these guys, and then you can figure it out. So, one of the things that we need to know for sure is what is the apparent charge of this species, and it is 0. So all of the oxidation states, the total number of electrons involved here, plus, minus, whatever, has to equal 0. Everything has to be accounted for and equal to 0. So sodium, okay, this is obviously an ionic compound, sodium and phosphate, PO3 anyways, phosphite, I guess. So sodium has a +1 charge here, right? Now, listen, I'm going to do this. I'm going to do a charge for each atom on top. So sodium has a +1 oxidation state. But involved in this compound, there are 3 sodiums. So guess what? The overall electronic accounting for sodium is +3 because there's 3 of them in the compound. So again, this is what I will do. I would encourage you to do this as well to keep track. But the oxidation state for the element goes on top. The total charge, or the total sort of accounting for the electrons that that element would carry in the compound, I'm going to put that number underneath, +3. And now why do I need that number underneath? Because remember, all of these charges underneath have to add up to 0. Well, what? Have to add up to 0. Okay, so right now I've got 3 already, okay? Now, the phosphorus, I don't know what I have here, but I do know what I have with oxygen. It's a -2 oxidation state for each oxygen. Because there's 3, I have a -6. You see that? So the total accounting for the electrons for the oxygens in this compound would be -6. There's 2 oxygens, each having a -2 oxidation state. So now I've got -6 here as well. Okay, so now this becomes a little bit more straightforward. I can solve for my P now. You see how I don't know what P is? But I do know that +3 plus the oxidation state for P plus -6 has to equal 0. So what does P have to be? Well, it would appear that it should be a positive 3 charge. There's 1 phosphorus. These need to add up to 0, so I'm missing a positive 3 there. So phosphorus has an oxidation state of plus 3. You see that? Plus 3 oxidation state. Yay? Nay? So-so? Questions? Okay. All right. Okay, let's do another one. Very similar. Each hydrogen. Well, this is sort of an ionic. It's this phosphoric acid, looks like. Or, well, it's got a -1 charge there, looks like. Okay, so anyways. +1 here. There's 2 of them. So this is going to be an overall +2 carried by the hydrogens here. I don't know what phosphorus is, but I can figure out what the oxygens, how the oxygens behave here. So these are -2 times 4 is -8. So I've got a total of -8 in this compound. Now, +2 plus unknown plus -8 has to equal, the apparent charge here is -1. Okay. Now you could solve like a traditional methods here, solve for x. There's 1p, so this is going to be 1x, right? So I could add 8 to both sides to get 7. I could subtract 2 to get 5. So let's see, does it make sense that +2 plus 5 minus 8 is -1? 2 plus 5 minus 8, does that equal -1? Yeah, it sure does. So guess what? Phosphorus here has an oxidation state of +5. And that tells us something too, that phosphorus and other sort of non-metals there can have multiple oxidation states, just like some of the metal ions can have multiple ionic charges, right? So those electrons are tricky, right? The number of electrons that an element can sort of handle or accommodate can be different, right? They're very active, very wild. There's certain tractions that work, some that don't. And so the electrons, how do they behave? Where are they sort of localized? Phosphorus can have multiple oxidation states, as we see here. All right. So here are the solutions here, sort of written out. We have a +3 and a +5. Okay. So I will turn your attention now to these text questions. And I think I should have those on your handout package that you have if you're in my class here right now. So I'm going to get you to work on 5 through 8, please. Doing a lot of the same things that we have done here in this lesson. So here's your homework, and I'm going to give you a little bit of time to work on that right now. Any questions before you embark on this? All right. Okay, so hopefully you've had a chance to take a look at these questions 5 through 8. I will show you solutions to 5 through 8 here. So here's the solution to number 5. A is +7, B +5, C +3 for these elements. And here's number 6. And here's number 7. Here's number 8, last one on your assignment here. Okay, I'm going to comment a little bit further on 7C, this hydrazine. This is called hydrazine. Is it frozen? Sorry. So because hydrogen is written second, you might think that it's a negative ion, and hydrogen does make a -1 ion at times. Hydrogen, but nitrogen will never, I don't think it's ever going to be a positive oxidation state. I could be wrong, but it's very, very seldom. Hydrogen is +1 the majority of the time. So if you had a +2 here, I wouldn't fault you too bad, but it is actually -2 because we do start with the hydrogen being +1 here, so that makes it an overall +4 charge, and then 2 hydrogens have to be -4, so each hydrogen is -2, and that's the way they get that. So that's hydrazine. Hydrogen is positive 1 still in this compound. It is a bit strange that it's written this way as well, but that's the way that it's written for hydrazine. But yeah, that's a tricky one. Okay, so if we look at B as well, guys, you might, I don't know where you're going to start here. You might start with this as a +1, this is a +4. I'm not really sure, but what you probably should do is recognize that this is an ionic compound. So in an ionic compound, this K is going to be +1. The Cn is going to be an ion of -1. This is cyanide ion, that's -1. So this is a bit tricky, but I think you should look at this as an ionic compound that it is. So then if you focus on the Cn -1, then we have +4, and nitrogen would be -3 then, to get -1. No, that's not right. Then, +4, that would be +1. KCN, oh, I see. Let's just see. If this was a +1 and this was a +4, this should be a -5. Some of you might have done it that way. If we focus on this, this should be a -5 as well. And I have a -3 there. Okay, so let's go back to the rules. Let's just check the rules real quick and see if we can find out why that is. Okay, so after a little bit more research here, if you said -5, I wouldn't fault you. However, between these three, K, C, and N, K really wants to get rid of an electron very strongly, so +1 here. N would be the next in line to attract electrons. C is in the middle of the table, periodic table, so it would be the one that would fluctuate most with the oxidation state. So N will have a higher attraction to electrons than does C. So instead of saying C is always +4, you have to go to N next and say, you know what, N would be +3, and then C would have a different oxidation charge than, let's say, +4, which you might expect. So this would be what, a -3, sorry, -3 here. It's a -3. So it'd be a +2 charge here for carbon. So yeah, so nitrogen has a greater attraction for electrons than does carbon, so it would keep its -3. Nitrogen would keep its -3 charge. Okay, yeah, so 7, B, and C I see are tricky. Any other of those questions that you had problems with? Yeah, those are tricky ones.